Welcome to everyone to this tutorial, and thank you for being here. So in the next 1 hour, I will go through how MIMO is implemented in Wi-Fi networks following the IEEE 82.11 standard. As I said before, the slides are available in my website, so you can just go in the teaching section here and you will find the slides if you want to download them. And I want to start from making clear the learning objective for this tutorial. So what will you learn, I hope, at the end of the tutorial is to understand the difference between a system with a single antenna at the transmitter and the receiver, so a single input, single output system, with respect to a system where we have multiple antennas at the transmitter and the receiver side. So multiple input, multiple output system. Actually, MIMO is only one of the typology of system with multiple antennas, because we may have also systems that have only multiple antennas at the receiver side and a single antenna at the transmitter side. So we will have the so-called SIMO system, or multiple antennas at the transmitter side and a single antenna at the receiver side. So all these multi-antenna systems allow us to improve the performance of wireless networks, and specifically in 3 aspects. So the first one is that they allow us to improve the robustness to fading by leveraging the diversity provided by the multiple antennas. Second, they allow us to increase the data rate by leveraging the multiplexing gain that we may have, increasing the number of antennas in the system. And third, they also allow us to reduce interference by using directionality. Actually, in this tutorial, we will focus on the first 2 gains, so the diversity gain and the multiplexing gain, because we will focus on the sub-6 portion of the radio spectrum where Wi-Fi networks operate, while the directionality is mostly used in the millimeter wave portion of the radio spectrum to create beamforming, so to focus the transmitted power toward a specific direction or receive the power through a specific direction. So this is the objective, and I hope that at the end of this tutorial, you will have clear in mind how we can leverage multi-antenna systems in order to improve the diversity and to improve the multiplexing. So to do that, I want first to start from the basics. So from the MIMO channel model, and to do that, I will briefly overview the how we can build how we can design the MIMO channel model. Actually, this is a technical tutorial, so I assume that all of you are familiar with wireless networks and with wireless transmissions. So here it will be a very brief introduction. Then we will move on and take a look at the benefits of using multi-antenna systems, specifically from the point of view of the diversity and multiplexing. After that, we will go into the detail of how MIMO is implemented in Wi-Fi networks, so following the IEEE 82.11 standard. And finally, I will conclude showing you some of my research about the potentiality and the weaknesses of the channel sounding procedure implemented in Wi-Fi networks, that is the procedure used to obtain an estimate of the MIMO channel, and then some open research challenges that I think deserve further investigation for next generation MIMO networks. If you want to go deeper into the detail of this topic, here you have some references. So 2 books and then the standard, so the most updated one that you can download without a subscription, so the 82.11 2020 edition and the 2021 amendment, that is the one followed by Wi-Fi 6 devices. And also in the different section in the tutorial, you will find the references for the first 2 books, so how you can find the different information. Okay, so I think we can get started. with the definition of the MIMO channel model. So actually, to define the MIMO channel model, we have to start from the way radio signals propagate in the environment. And radio signals propagate following the multipath propagation effect. This means that the receiver device will collect several copies of the transmitted signals due to the different objects and to the different obstacles that the signals encounters in its way from the transmitter to the receiver. So we may have the line of sight path if the transmitter and the receiver see each other. And then we can have all the different reflections due to the objects and the walls, the floor, and so on and so forth. Here we have an example of a first order reflection where we have only one reflecting surface. And we may have also higher order reflection. For example, here we have a reflection with two bunches. In addition to the multipath effect that introduces fading in the channel, we have also the effect of the path loss that is linked with the distance between the transmitter and the receiver. And the path loss increases with the logarithm of the distance, as you can see in this plot, where we show the ratio between the received power of the signal and the transmitted one. And then you see the impact of the shadowing. The shadowing is due to the absorption of the energy of the signal from different objects that are in the environment. And at the end, the combined effect of the path loss, the shadowing, and the multipath fading is the one in blue here in the figure. So from a mathematical perspective, if we model the transmitted signal in this way by considering the baseband signal up converted to the carrier frequency, and we transmit the real part of this signal, the received one can be modeled in this way, where we have a combination over all the different copies of the signals received by the receiver antennas. And each copy is characterized by an attenuation that is due to the path loss and the shadowing, and a delay that is linked with the multipath fading. And the delay is affecting both the shape of the signal and also introduce a phase shift. In addition, we have also a phase shift linked with the Doppler effect that is due to the movement of the transmitter, the receiver, or objects in the environment. And at the end, we can obtain the function that links the transmitted signal with the received one, that is the channel impulse response. And the channel impulse response, as you can see here, defines how the different multipath components combine at the receiver and to generate the received signal. To characterize the channel impulse response and to characterize the fading that the signal is undergoing, we can take a look at the power delay profile, that is the autocorrelation of the channel impulse response. And we can identify two different situations by taking a look at the power delay profile in the time or equivalently in the frequency domain by applying a Fourier transformation. And the two situations are linked with the value of two quantities that are linked one to the other. In the delay, in the time domain, the variable that tell us how the fading behave is the delay spread. That is the difference between the first and the last multipath component with significant energy. Equivalently, in the frequency domain, the fading is characterized by taking a look at the coherence bandwidth. The coherence bandwidth is 1 divided by the root mean square of the delay spread. And as you can see here, we may have two types of signals. The first one, that is the one here in dashed line, is when the channel bandwidth, the signal bandwidth is smaller with respect to the coherence bandwidth. In this case, in this case, all the components of the signal will experience a very similar fading. And so in this case, we call the fading undergoes by the signal as flat fading. The other situation is when instead we have a signal that has a bandwidth that is comparable or higher with respect to the coherence bandwidth. In this case, the components of the signal that are spaced apart by a quantity that is comparable to the coherence bandwidth will experience very uncorrelated fading, as you can see here, where the correlation is actually 0. And in this case, we talk about the frequency selectivity, so frequency selective fading. Actually, when we want to design a communication system, we want to be in this situation, so where we have a flat fading, and this is also how we then model our MIMO channel. Taking a look at it in the time domain, narrowband fading means that the symbol time is higher with respect to the delay spread. So this means that all the different copies from the multipath propagation will arrive before the start of the new symbol, so we don't have intersymbol interference. And by using this assumption, we can do an approximation in the model of the received signal, because we can approximate this contribution of the signal into the same signal in the baseband component of the signal. And this way, we can also simplify the expression for the channel impulse response that will no longer depend on the delay. Will no longer depend on the delay. So we have this expression for the channel frequency response when we are in narrowband fading situation, and the channel impulse response is simply defined by the combination of all the different components due to the multipath that are characterized by an attenuation and a phase shift linked with the delay of the path that is associated with the length of that multipath component. So finally, we can define our narrowband MIMO channel model. We will consider through all the tutorial a system where we have M transmitter antenna and N receiver antennas, and the model for the MIMO transmission in the frequency domain is identified in this way, where we have X, that is the transmitted signal, that is an M-dimensional vector. Y is the received signal, again in the frequency domain, and this is an N-dimensional vector, and they are linked by the channel frequency response, that is an M by M dimensional vector, where each element of the channel frequency response is the Fourier transform of the impulse response for that specific link. So we will have one channel frequency response for the link from the first antenna at the transmitter to the first antenna and the receiver, one from the first antenna and the transmitter and the second and the receiver, and so on and so forth. So we will end up with this N by M dimensional matrix. And then we have additive noise and also an attenuation factor linked with the SNR for the different links that we have here. So this is the model that we will use through the entire tutorial. And we can now go deeper into the detail of the benefit of using multi-antenna systems. So we will start from the diversity and then move to the multiplexing. So starting from the diversity gain, what does it mean? So the diversity means that we transmit the same signal through independent fading channel, or we received the same signal from independent fading channel. In this way, we are adding redundancy because we are transmitting or receiving the same signal several times. And this redundancy helps us in improving the robustness of our system, because it is very unlikely that all the independent fading channel will experience deep fades simultaneously. So at least one of the channel will be good and will allow us to properly decode the stream. So if we transmit from different independent channels, we are applying the diversity at the transmitter, but we can also apply it at the receiver by using several independent fading channels to receive the signal, or also we can combine the two. Actually, here I kept it general because diversity can be leveraged both in the space domain by using different antennas spaced apart by a distance that is higher than the wavelength divided by 2 to create independent fading channel. But diversity can also be leveraged in other domains. So for example, in the angle domain, by transmitting signals through different directive antennas, or in the frequency domain, by considering different carrier frequencies and transmitting the same signal over the different carrier frequencies. Again, in the time domain, so transmitting the same signal several times in time, or also by using different antennas with different polarizations. So now we will focus on the space diversity. So we will see how we can improve the robustness by using different several antennas at the transmitter or at the receiver side, or both. So starting from the transmitter, here we have an example of a system where we have 2 transmitter antennas and 1 receiver antenna. So we have a signal that we want to transmit, that is X. What we want to do is to use these 2 antennas in order to improve the robustness of our system to noise and fading. And 2 approaches that can be applied without having any knowledge about the channel here are spatial expansion and space-time block coding. In the spatial expansion, we take the signal and we transmit the signal through the different antennas by applying different cyclic shift. While in the space-time block coding, we use some specific codes, for example, the Alamuti code, in order to transmit the different copies of the signal by leveraging both the spatial diversity provided by the different antennas and the time diversity. But we can also do better than this if we know the channel here. So if we have some information about the way the signal propagates from the transmitter to the receiver, we can use this information in order to properly modify the transmitted signal before transmitting it through the different antennas and compensate for the channel impairments. And this is called transmit beamforming. And it is implemented by modifying this signal and combining it at the different antennas through some weights. Here we have W1, and at the other antennas we have W2 before transmitting it through the channel. And the idea is that this W2 will compensate for the impairment of this channel, and W1 for the impairment of this link from the first antenna to the receiver antenna. And at the output, we will have a signal that combines the 2 transmitted signal in order to improve the SNR. So we will have a signal that is highly, we will have higher chance to decode this signal with respect to transmitting only a single copy. So the same can be applied at the receiver. Here we have an example with 1 transmitter antenna and 2 receiver antennas. An approach in this case is to apply maximum ratio combining. That means that we take the signal received at the 2 different antennas and we apply some weights, this time at the receiver antenna, in order for compensating for the channel impairments introduced by the different links. And then we combine the 2 weighted signals. So we have a weighted sum. And this this allows to improve the combined signal to noise ratio and to improve the decoding by doing the equalization to retrieve the original transmitted stream. So this is how diversity can be implemented in wireless systems. Let's now take a look at multiplexing, and then let's see what we can do with both of them. So multiplexing, while in diversity, what we did was to transmit the same signal over the independent fading channel in order to improve robustness. Here instead, we want to transmit different streams over the independent fading channel in order to improve the data rate. So we want to simultaneously transmit multiple data streams instead of improving the robustness. And here, an important step is at the receiver side, the demultiplexing that will allow us to retrieve the different data streams and separate them out. Again, also in this case, multiplexing can be implemented both in the space domain with the space division multiplexing by creating the independent fading channel by spacing the antenna by more than the wavelength divided by 2, but can be implemented also in other domains, for example, in the frequency domain. An example is the orthogonal frequency division multiplexing, or FDM, where we have the bandwidth that is the available bandwidth that is divided into small sub-channels, and we are transmitting different OFDM samples in each of the sub-channel. Okay, so let's focus on the space division multiplexing, and let's see how this can be implemented. The idea actually is that we want not to transmit the streams sequentially one after the other, but we want to transmit them simultaneously in order that they will arrive at the receiver faster, and in this way we increase the data rate. So let's assume that we have a number of spatial streams that is NSS. If we want to transmit this number of spatial streams, we should have a system where we have a number of transmitter antenna that is at least equal to the number of streams that we want to transmit, and the same applies to the receiver. So at the receiver, we should have a number of receiver antenna that is at least equal to the number of spatial streams that we want to receive. Here, we have two examples where we have 2 antennas at the transmitter and 2 or 3 antennas at the receiver. Actually, in both of the cases, the maximum number of spatial streams that we can transmit is 2, because the number of spatial streams that we can transmit is limited by the smaller between the number of transmitter antenna and the number of receiver antenna. So here I want to stress that we are transmitting different streams, while for diversity we were transmitting the same stream through the different antennas. So how we can implement the equalizer at the receiver? The simple approach that is the one that is also adopted in wireless networks and specifically in Wi-Fi is to apply a linear equalizer. So we take the received stream and we apply a equalization matrix that here is indicated by G to retrieve the transmitted data streams. There are mainly 2 approaches that can be applied for equalization. The first one is a zero forcing equalization. Yeah, that means that we take the channel matrix H and we invert it. Here is the pseudo inverse because H can also not be square. And the other approach is to also take into account an estimate of the noise. Here is the noise covariance in order to alleviate the impact of the noise at the receiver. Okay, so to summarize, what we saw so far is that with the space division multiplexing, we are using the different MIMO channels in order to transmit several data streams simultaneously to increase the capacity of the system. While with diversity, we are combining coherently the gains over the independent fading channel in order to improve and to increase the robustness to fading of our system. And now the question is, should we use MIMO for multiplexing or for diversity? And the answer is that we don't have to choose, because we can combine them. So we can combine multiplexing gain and diversity gain. So for example, at the receiver, we can use some space dimension for diversity and the other for multiplexing. And we can do the same at the receiver. For example, if at the receiver we have a number of antennas that is higher with respect to the number of spatial streams that we have to decode, we can use the other degree of freedom in order to improve the diversity of the system. And the diversity is increased by the difference between the received antennas and the number of spatial streams. So how can we implement this? This is the scheme that allows us to combine diversity and multiplexing. And it is called transmit beamforming. We already saw it when we talked about the diversity gain. Here you have an example where we have 2 streams that should be transmitted through 3 different antennas at the transmitter, and at the receiver we have 2 antennas that are used to decode the 2 different streams. The way the multiplexing and the diversity are combined is by using these weights that are called precoding weights. And these weights allow to transmit all the different streams together and transmit all the stream through all the antennas. So as you can see here, stream S1 is transmitted from antenna 1, then it is transmitted from antenna 2, and it is transmitted also from antenna 3. And if you think about it, this is the diversity gain, because we are transmitting it through the 3 independent fading channel. But also we are transmitting the 2 streams simultaneously. We are transmitting both S1 and S2 simultaneously. And this is the multiplexing gain. So by using these precoding weights, by combining the different streams at the different antennas in some way that now we will see how, we are able to improve both the, to increase both the multiplexing gain and the diversity gain. And these precoding weights are the ones that allow us to obtain the independent fading channel. And this is how MIMO is implemented and is leveraged in IEEE 82.11 networks, so in Wi-Fi. In Wi-Fi, the multiple antennas available mostly at the transmitter side, so at the access point, are used to improve, to increase the multiplexing and the diversity. So how are the precoding weights obtained? As we already mentioned before, if we have a knowledge of the channel, we can use it in order to combine the streams in such a way that we compensate for the channel impairments. And this is how the precoding weights are obtained. So to do that, we decompose the channel frequency response through singular value decomposition. And we retain only the right unitary matrix, that is a matrix that is M by M, where M is the number of antennas at the transmitter side. And this matrix represents an orthonormal basis in the space R to the M. So we can use the different columns of this matrix, so the different orthonormal vectors in the column of this matrix, to weight the different streams and create orthogonal streams. And this is how it is done. So the precoding weights are obtained from this matrix by selecting only the columns that we need. Here we have a maximum of m columns, but we said before that we can transmit only also a number of streams that is smaller with respect to the available transmitting antenna. So we will select the columns that we need for our spatial streams, and we use this matrix to combine the different spatial streams differently at the different antennas in order to create orthogonal transmissions. And at the receiver, what happens is that we have, as we said before, to demultiplex the streams that we receive, because here they are combined, the different streams are combined at the different receiving antenna. And to do that, we apply a linear receiver through zero forcing, as we saw, we introduced before. But actually here, we are not inverting only the channel matrix, but we are inverting the beamformed channel. So the channel matrix plus the precoding matrix. So this HW. And actually here you have the pseudo inverse of this HW. So this is how we can leverage diversity and multiplexing. So let's now see how this is implemented in Wi-Fi networks. So here is the general pipeline of Wi-Fi transmission, starting from the bits here on the left to the radio frequency signal here on the right, that are transmitted through the different antennas. Actually, we will focus now on this block, that is the OFDM MIMO modulation, where we have here the spatial mapping, where the precoding is applied. So the different streams are multiplied by the precoding weights, and then an inverse discrete Fourier transform is used in order to obtain the different OFDM symbols. So here we are talking about two multiplexing techniques, because we not only have a multiplexing in the space domain, but we also apply multiplexing in the frequency domain through OFDM. And so our channel matrix should be characterized for the different links between each transmitter antenna and each receiver antenna, but also on the different subchannels. So the channel matrix at the end will be three-dimensional, because we are adding the dimension of the OFDM subchannels. But the expression is the same that we saw before for the narrowband MIMO channel model. So we have the sum over the different multipath components, and each multipath component is characterized by an attenuation and a phase shift linked with the length of the path. Okay, so there are two modalities in Wi-Fi networks to leverage the diversity and the multiplexing gain provided by MIMO networks. The first one is to transmit multiple streams to a single receiver, and this is the so-called single user MIMO. This was introduced with the Wi-Fi 4, so the 82.11n. While after that, with Wi-Fi 5, they also introduced multi-user MIMO. That means that we can transmit multiple streams to multiple receivers, so to multiple beamformees, in the downlink direction, so from the access point to the users. And also in Wi-Fi 6, that is the 82.11ax, they also enable different users to transmit simultaneously in the uplink direction several data streams. So in the next slides, we will focus on downlink multi-user MIMO and single user MIMO, because for the uplink multi-user MIMO, there are some, well, it is implemented a bit differently, but it is derived from the downlink multi-user MIMO. So the three steps that are followed to implement this operational mode are, at first, that we need to estimate the channel. So as we said before, we need to have knowledge about the way the signal propagates from the transmitter to the receiver in order to apply precoding, so to linearly combine the different streams to be transmitted in such a way that we compensate for the channel impairments. And then the last phase is at the receiver side, where we have to retrieve the data streams by applying the multiplexing technique through the equalization. So let's go into the detail of these steps, starting from the channel sounding. So how we can estimate the channel frequency response, the way the signal propagates. So channel sounding is implemented in Wi-Fi network through a procedure that is triggered by the access point that transmits a null data packet, that is a packet that does not contain any data, but only contains some training fields that are symbols that are known by the receivers. And so the receivers can use these known symbols in order to estimate the channel. So they can estimate the channel frequency response. And after doing that, they have to transmit back the channel frequency response to the access point. But to do it efficiently, the stations will first compute a compressed representation of this channel frequency response. And this is done by first decomposing the channel frequency response through singular value decomposition. Then, as we said before, we can retain the right unitary matrix in order to obtain the orthonormal vectors to precode our streams. So we will keep only the first number of vectors that are equal to the number of streams that we want to transmit. And then this matrix that we will call it V, as it is called in the standard, will be further compressed before being feedback to the access point. Here you can see also the different packets in the time domain, how they are transmitted by the beamformer and the beamformees. So the compression is implemented for two reasons. The first one is because we want to reduce overhead, because we don't want to occupy the channel for control data. We want to transmit as many data as possible and reduce the amount of control data transmitted over the channel. And the second reason is that for the precoding, we have to use the most updated channel information. So we don't want to use outdated channel information that arrive at the access point after a lot of time that actually it is not useful to compensate for the channel impairments, because in the meantime, the channel changed. And the compression is performed by applying some mathematical transformations that are called Givens rotations. And through these transformations, we obtain some quantities that are called beamforming feedback angles and are identified by these symbols, so psi and phi. And then these angles are quantized in order to further reduce the airtime overhead. And at the end, the stations, instead of transmitting the big channel frequency response, are only required to transmit back these small beamforming feedback angles. So this is the algorithm that is used by the station to compute the angles. I will not go into the detail of it. If you are interested, you can find the detail in the books or in the standard or in this paper. But only to show you where the beamforming feedback angles are obtained. They are here. And these are the transformation matrices that are used for the Givens rotations. So here is a screenshot from Wireshark, where I captured a feedback packet, a beamforming feedback packet. This is the structure of the packet. So there is some control information, and then there is the compressed beamforming feedback. By taking a look at the beamforming information, you can see here the number of spatial streams. In this case, we have 2 spatial streams. Then we have the information about the number of transmitter antenna. Here we have 4 transmitter antenna. The bandwidth, these 2 indicate that we are working with 80 megahertz. And then we have other information that allow us to properly decode the beamforming feedback matrix. And in particular, this through the codebook information and the feedback type. The codebook information tell us how many bits are used to quantize the phi and psi angles. And this is to be read together with the feedback type. Here is a screenshot from the standard where you can see that for this feedback type, so single user MIMO, if we use a codebook 0, it means that we are using 4 bits for phi and 2 bits for psi. And then we have other combination for different codebooks and for multi-user MIMO. And this is the information we are looking for. So the phi and psi angles that you can find here. And in the standard, it is written how the station should put the information here in order that the access point will be able to decode the information and use this information for precoding. An important note here is that these angles are actually transmitted unencrypted, are feedback from the station to the access point unencrypted. And I will show you that this is both something that researcher can use, but is also a weakness of MIMO networks. And here, to conclude, is an example of the phi and psi angles that we capture through this tool. Actually, you can capture the angle through Wireshark. This is a tool that allows to automate the procedure. Okay, so after channel sounding, so now we are at the point where the stations obtain compute the information about the channel, so how the signal was modified from the transmitter to the receiver, and transmitted back this information to the access point. Now the access point have to use this information to modify the transmitted signals at the different antennas in order to compensate for the channel impairments and reach the required multiplexing and diversity gain. So for precoding, the first thing that the access point has to do is to take the compressed information, so to take the beamforming feedback angles and reconstruct the V matrices. And the reconstruction is done by reverting the given rotations by using the matrices that I showed you before, so the D and G matrices. Actually, to do this, we also, to revert back the complete procedure and obtain the V matrix, so the subportion of the right unitary matrix of the singular value decomposition of the channel. We also need another matrix that is here indicated with tilde D. But actually, some research showed that obtaining the precoding with this V matrix or with the V tilde submatrix is almost the same from the point of view of the performance. And for this reason, this second matrix, the D tilde matrix, is not feedback. Again, in view of reducing the overhead for feedback transmission. So what it is done here at this point after having reconstructed the V matrices, so the V matrices are reconstructed for all the different beamformees that feedback one after the other, the beamforming feedback angles. And having all the different V matrices, they are combined into a big matrix of dimension M by NSS, where NSS is the total number of spatial streams summed over all the beamformees. And this matrix is then used for precoding. The precoding is applied in this way. So it is the combined matrix that is formed by all the different orthonormal vector feedback by the different beamformees. And we also have here a normalizing factor, and this is needed to enforce that each transmitted stream is orthogonal to the channel between the access point and the unintended receivers, to not create interstream interference. So to make an example, here, for example, we have this spatial stream S1 that is transmitted after through the first antenna with a combination factor that is W11. This factor is selected through this procedure in such a way that it cancels out with this channel gain. So at the end, here R2 will have a minimal contribution from this path. So W11 multiplied by H21 will be almost 0. And this is to reduce the interference that the different streams cause to the other streams that are transmitted simultaneously. So at the receiver, what we have is at the end, so what we have can be modeled by this formulation, where we have X that contains all the different transmitted streams, W is our precoding matrix, H is the complete channel matrix that we have here, and then we have the contribution of the attenuation linked with the signal to noise ratio and also the noise. So, okay, here I only want to show you some of the research that we did about the errors that the quantization introduced in the reconstruction of the V matrix. And here you can see a qualitative experimental evaluation where we have the reconstruction of the V matrix from the beamforming feedback angles for the first stream here on the top for 3 different antennas, and the second stream here on the bottom. And as you can see, the second stream is much more noisier with respect to the first stream. And this is linked with the propagation of the error in the algorithm that I briefly show you before, where because the beamforming feedback angles for the different streams are obtained by starting from the beamforming feedback angles of the first streams. And so the error propagates and the reconstruction of the V matrix degrades. And these also have an effect on the bit error rate in the different streams. So starting from the first to the last, we will have a slight increase in the bit error rate. So we arrived at the last operation that we have to perform in order to implement MIMO networks in Wi-Fi, that is data decoding. And this is implemented at the receiver by estimating again the wireless channel by using the training fields that are included inside the beamforming data pack, the beamformed data packets. Actually, what we estimate now is not only the channel H, but it is the beamformed channel. So we will estimate the H multiplied by W channel. And with this information about the beamformed channel matrix, we can obtain an interference cancellation matrix to equalize the signal. And it is obtained, as we already saw several times during this tutorial, by inverting this channel matrix. So the channel matrix, the beamformed channel matrix. In this case, we are also accounting for the covariance of the noise. So this is a minimum mean square error linear equalization. Okay, so this concluded the overview about the steps to implement the MIMO networks. So we are going going to conclude this tutorial. But first, I want to show you some results that we obtained in our research. And what we found is that the fact that the feedback is transmitted back unencrypted by the station to the access point can be used for implementing some useful application in Wi-Fi networks, because the feedback can be used as a proxy for the channel frequency response. And we tried to use it for two different applications. The first one is to fingerprint the devices, so to obtain a fingerprint at the physical layer. And then we also try to use it for wireless sensing, so to obtain some information about what is happening in the environment. But as I introduced before, this is also a weakness, because the fact that the feedback is transmitted back unencrypted opens also the door to adversarial attacks that can try to alter the communication system. So here you have the references if you want to take a look at the two different applications that I mentioned. For what concerned the fingerprinting, what we did was to capture the beamforming feedback angles and obtain back the V matrices, and use the V matrices to obtain a fingerprint of the transmitter device. So our intuition was that the imperfection of this device percolates in the null data packets and also in the feedback angles, and so we can try to characterize the hardware imperfection of this device by taking a look at the compressed beamforming feedback. And the second application is about using the beamforming feedback angles directly, so without converting back to the V matrix, and using them as a proxy for the channel frequency response to obtain information about the environmental changes. And then regarding the weakness that I was mentioning, what we discover is that if a malicious user in the network eavesdrop the channel feedback transmitted, again unencrypted, by a legitimate station, it can craft a malicious feedback that at the end will lead the access point to obtain an incorrect precoding. And this incorrect precoding means that the different streams are not orthogonal to the channel between the streams, between the access point and the unintended receiver. In this way, they will create interference at the legitimate station, and the legitimate station will see a degradation in the throughput. Here you find also in this case the references, and there is also the recording of the plenary workshop in Palermo, where I presented this attack. And so to conclude the tutorial, I want to only mention two open challenges that I see in the implementation of MIMO networks, and especially in Wi-Fi. The first one is the security challenge, and I just said why this is a challenge, because the fact that the feedback is transmitted unencrypted opens the door to unintended malicious users. And the second challenge is the scalability, because so for next generation application, what we need is to increase the number of antennas to increase the multiplexing gain. But actually, the channel sounding does not scale well with the number of antennas, because the computational complexity of the channel sounding grows as m to the power of 4, and the airtime overhead grows as the square of the number of antennas at the transmitter. And so you can understand that we have a bottleneck and we can't increase the number of antennas as much as we want. And in fact, while in the Wi-Fi 6 standard, so the 82.11ax, in principle, the devices should support up to 8x8 MIMO. Commercial devices as only support 4x4 MIMO. So I think that there is a lot of work to do in making MIMO networks really scalable with the number of antennas and also secure from the point of view of the control information that is transmitted unencrypted. And this is also what I'm working on in my research. Yeah, with this, I think that I hope that you enjoyed the tutorial and that you now have some idea of how MIMO can be implemented in Wi-Fi and what are the benefits that we can have from multi-antenna systems, and also some brief overview of open challenges that should be solved for us as researchers. And with this, I thank you for attending the tutorial.